All right. Can you also see the screen? Okay, so today we'll be starting with magnetism, right? And let me open your chat here so I can see that as well. All right. Okay. So actually, before we do that, is there any questions from the quiz that was shared with you last time on capacitance? Was it all okay? Was it clear? Any questions from it? Anything that was not clear in the solution manual? Is there any specific problem from that quiz that you would like me to go through again? If not, then we'll continue with magnetism. Okay, so I think no questions, right? Okay, so for magnetism, you must be familiar with a couple of things from your AS level on magnetic fields, but we'll start our discussion with magnetic fields, right? Now, magnetic field is basically a region of space where any material experiences magnetic field, right? And now what does that a magnetic field or magnetic effects, I mean, right? And what does that mean? First of all, experiencing magnetism, what does that mean, right? So for that, we'll need to also define magnetism and where does magnetism comes from. So if you remember, for electric charges, if I had a positive charge, just having this information told you that there would be some electric field around this charge. And if it's a positive charge and it's static, it's stationary, it's not moving, that would mean that there would be some electric field lines, and they were defined as coming out of a positive charge, right? And so if they're coming out of a positive charge, that means they should be going into a negative charge, as that is the opposite for that. Now, if the charge is static and it's not moving, then the only field that it will experience is electric field, right? So for an electric field to be experienced, you need a charged object. It could be positively charged or negatively charged, but it should be charged. And if it is charged, that would mean that would imply that there would be some electric field around that charge. So what could there is something that you could do to make this dynamic, right? So it just gives this charge a push or something. So the charge may start moving, right? So suppose that if the same charge now started to move in a given direction. So it's just an experiment to see what would happen, right? So let's now not keep the charge stationary, but let's give it some velocity and let's move it in some particular direction. When this happens, there is a new field that can be experienced, which is called the magnetic field, right? So for magnetic field or magnetism to exist, there should be a charged object in motion, right? So magnetism comes from the fact that if I have a motion of a charged particle, right? So there are two conditions. One, that the particle should be charged, and the second condition is that it should be moving. If it's just charged, then there will always be an electric field, right? And if it's now also moving, there would also be another type of field, which is called the magnetic field. And basically, electric and magnetic fields are two sides of the same coin. Why do I say that? It's because motion is relative, right? So for example, if I'm standing over here and I see a car moving in this direction, right? So I'm observing, this is me, and I'm observing this car, which is moving in this direction. Suppose it's moving with some velocity of, I don't know, 80 kilometers per hour, right? And of course, there would be a driver sitting in the car, would be driving this car. I would see, if I measure the speed of this person who's sitting in the car, because he's inside the car, so he's moving along or with the car, I would observe his speed to be this 80 kilometers per hour, right? But he would tell me, no, I'm just sitting still inside the car, and so my speed is 0 meters per second. I'm at rest, right? And then you can have multiple other examples as well to say that the motion is indeed relative. Is, for example, if I have a car, two cars, right? And they're both moving, for example, in some direction. And this would have some velocity. This would also have some velocity. Let's call it V1, V2. These two cars, they would experience or see each other's velocities as different, right? And to elaborate more on that, you can think of something. Suppose that if these two cars are traveling at same speed, suppose this is also, this is V and this is also V, and they're traveling parallel to each other. Let me bring this over here. Suppose that this is, it's like parallel. So they're traveling both parallel to each other. If they're both traveling parallel to each other, they would see each other as stationary, right? It would appear that the car next to them, which is parallel to them, if the velocity, magnitude of the velocity and the direction of the velocity is the same, then they would see each other as traveling with no velocities. Basically, v is equal to 0. So for them, the v will be 0, because this person in this one would see the other one as stationary. However, if again someone from the outside was observing both of them, he would record their speeds as v, whatever that speed v is, right? So motion is relative. Now, if motion is relative, and I say, let me fix this zoom. And if I say that magnetism, I don't say it, it's an experimental evidence that if a charged particle is moving, only then it experiences a magnetic field, right? Or magnetic effects or magnetic force. But motion is relative. For someone, motion could be, there would be no motion, and for the other person, there could be some motion, as demonstrated from this example. So that would mean that magnetism is basically, you can say it's not 100% accurate to say that, but it's kind of like an illusion, right? And so for one observer, coming back to these field lines and charges, for one observer, it could happen that one of these charges is just stationary, while the other, someone else who's observing these charges, for him, the charges could be moving. So one could be saying that there is no magnetic field, while the other says that there is a magnetic field. It doesn't mean that any of them are wrong. It's just that they're supposed to say relative to them, there is no magnetic field, right? And that's why we say, or I say that the magnetism and electricity is basically two sides of the same coin. And that's why, in fact, electricity and magnetism are unified together as well. That's why they're called electromagnetism. The study of both of these things together is called electromagnetism. And what that means is that both of these phenomena or forces, electricity and magnetism, are one in the same thing, right? So they're unified. Now, let's now talk about magnetic field, right? So by definition, it is a region of space where a magnet would experience whatever the spelling is, some type of force, and that force, we'll call it magnetic force, right? So for example, if I take a charge, again, I'll take positive charge, and this charge is moving. As soon as it starts to move, there will be some magnetic field lines coming from this charge. The field lines, as you're already familiar with that, the field lines are just imaginary lines, right? They do not really exist. They just help us, the arrows and the gap between the lines, they just help us to understand how much magnetic field there is and what is the direction of that magnetic field, right? So now suppose if this is a positive charge and it starts to move, it creates a magnetic field around it. And so I can draw that magnetic field. Something like, so I'll need another charge as well. So if there is a positive charge, suppose that this is some region of magnetic field, right? So this is not accurate right now, but suppose that there is some magnetic field region around this positive charge, and there is also electric field. So, right, electric fields are directly outwards. Now, suppose if I bring any material, now the condition is it could not be any material. It should be a magnetic material, basically, or a current carrying conductor. What is a current carrying conductor, by the way? Suppose that a wire, for example, I'm going to try to draw a wire, fat version of it. So suppose that this is a wire and there is some current flowing in this wire. What I'm saying is that I can call this a magnetic material. This current carrying conductor, a wire, I can call this a magnetic material. Can you, by whatever we have talked about so far, can you tell me why would this be a magnetic material? Anyone? Okay, free electrons. So basically, there are charges, but why is it a magnetic material? I think by free electrons you mean they're moving, right? So that's because those yeah. So the electrons in this wire, if it carries current, if the wire is just sitting there with not plugged into some potential different source or anything, then there would be no magnetic fields or magnetism over there, because the charges would be sitting still, they would not be moving. But once I provide that potential difference, that's when the charges starts to flow, and the flow of charges is just charges moving, which means that this would be then a magnetic material, or it would behave as a magnetic material or a magnet, right? So if I bring this type of a material inside this field line, this material experiences a force, right? And now I cannot right now. I cannot tell you the direction of this force. We'll talk about that in a bit. But it would experience, there would be some force experienced by this magnetic material. It's not some mysterious force or anything. This force comes from the magnetic field lines, or the magnetic field, right? Now, for a magnet, for charges, if you remember, there was, if I go back to this diagram, if you look at this positive charge, it was not necessary to have another negative charge combined with a positive charge. A positive charge itself could just live there, right? And then we would have a negative charge. So for positive charge, the field lines were defined as coming outside, and for a negative, they were defined as coming inside. But in magnetism, it's not really like that. For magnetism, as you might have heard about these magnets, they have north and south pole, right? You'll never see a magnet that only has one of these, right? Or just a north pole. For every magnet to be complete, for it to be a magnet, a complete magnet, there should be two poles, so that from one of the pole, the field lines can travel outwards and end at the south pole. So a magnet always needs a starting or an and an end point. You can think of it like that, right? So there is no such thing as just a north pole magnet. Something like that does not exist, right? And this comes from one of equations of Maxwell. Will not go into that, but so yeah. Now let's talk about the very important, we'll call them laws of magnetism. Is, again, if you remember, for electricity, we had positive and negative charges, and this thing defined those laws of electricity, which were that like charges repel and unlike attract, right? So we got a law for positive and negative, that was like charges will attract each other, and like charges will repel each other, and unlike charges will come closer together. And we discussed that in detail. In exactly the same way, there are some laws of magnetism, and so I'll write it over here. The first, again, it's the same as electricity, more or less, that like poles repel and unlike poles attract. Right. So let's consider this magnet, this one. Copy, I'll take it to the next page. Let's discuss some of the multiple magnetic field shapes, right? Magnetic field lines, or the shapes that these lines form, right? So shapes. So again, magnetic field is just a region where if particular specific type of force is felt, and that force is defined as the magnetic force. If I have this magnet which has two poles, north and south, again, we have discussed that there should be, both of these poles should exist together to form a magnet. Let me increase the size of this. The field lines look something like, so they come out of one of the poles and they end inside another one. right? Now, if we define North Pole as, so again, it's nothing, there's nothing special to this North and South. You could have just called them any other thing, right? But like, for example, there should be an opposite for that. For example, for positive, there was a negative. So for magnetism, we just call it North and South, right? So two opposite directions. So the field lines are just those imaginary lines which will show the direction of the force on a North Pole when it's placed inside a magnetic field. And it looks something like this, that it's coming out from the north and going into the south. And it will look exactly the same below as well. If I can draw this correctly, north to south, right? And around it, it's something like this, right? So this line is just, again, basically it's something like this, right? So we can draw it like, sorry, this should be coming out. Right. So this type of a magnet, it's called a bar magnet. And we can, now you might ask that where do we get this pattern from, right? This pattern of electric field lines, how do we know that it has to look like this, or does it looks like this? And it's pretty straightforward to figure out that pattern in this way, that we can check that experimentally. You can place a magnet on a table, and around it there are, so if you place some iron fillings or any conductor like thing, you'd see that given a little bit of time, it would form that specific pattern. And for a bar magnet, that pattern would look something like these lines that you can see over here. So that's where, that's basically telling you the direction of the force that is being exerted on those iron fillings. And that's why they're oriented in that specific direction. Right now, when we're drawing these magnetic field lines, there are two things that are to be kept in mind. So the closer the lines that are drawn, that means the more stronger the magnetic field is experienced over there. So if I draw this once again, this is north, this is south. So closer to the magnet, the magnetic field would be stronger, and further apart from the magnet, the magnetic field would be weaker. So that's why these lines that are closer, they represent stronger magnetic effects or strong magnetic force. And as the gap increases between these lines, that's where we have weak magnetic effects. Right? Now, suppose that if I have two magnets like this, and suppose that this is north, south, and this is south, north, right? And I bring these two magnets closer together. We know that the magnetic field lines tend to go from one of the poles to the other of the poles, and specifically from north to south, right? So the field lines between these two magnets would look something like this. So they would be just straight lines coming out from north and going into the south pole of the other magnet, right? And so as I move away from these magnets, the field lines, they tend to look something like this. And the further away I go, the weaker these field lines will become. The weaker the magnetic effects or magnetic force will become, right? So this is magnetic field lines between two opposite poles. Any questions from up till here? Okay, so let's quickly then talk about magnetic field around our current carrying conductor that we just discussed. Magnetic field for current carrying conductor. I'll just write it as CCC. Right. So and a current carrying conductor could be any wire, right? For example, I'll again just draw a straight line now. Suppose that this is a wire and it carries some current around it, not around it, through it, right? Suppose if the direction of the current is in this way, right? It's upwards. In that case, the magnetic field that is produced because of the flow of charges, and so the direction of current is just telling me the flow, the direction of flow of those charges. So charges are moving in upwards direction. When that happens, the magnetic field that is created around this wire is in this circular direction, that it runs counterclockwise, right? So which would mean that if I bring any other charged particle in near this wire, it will go around this wire in this direction, right? So if I were to bring a charged particle, suppose this is some charged particle Q, and this particle would experience, if it's moving, it would experience that magnetic field and it would start going in a spiral along this wire, right? And then there is, if I reverse the direction of the current, that would just mean that the flow of charges, the motion of charges has been reversed, which would just change the direction of the magnetic field. And now the magnetic field would be the opposite of what it was before, and that is clockwise direction. Again, if I bring any other charge which is moving, so a moving charge in this vicinity of this magnetic field, it would experience a force in this direction and it would start again to go in spiral if it's moving, right? Now, there is, for all current carrying conductors, there is something that is called, it's just a trick to figure out where would be the direction of the current, and what if for that, what would be the direction of the magnetic field, right? So if I have a straight wire that I've just drawn, then there is a rule that's called, I mean, right hand rule, or you can say right hand grip rule, which just means that if I hold this conductor, right, so I'll curl my fingers around it, and if I do that, then the curl of the fingers will be telling me the direction of magnetic field, while the thumb tells me, the thumb points in the direction of flow of charges or the current, right? And you can check that by looking at any of these wires. If I apply that right hand grip rule, if I grip this wire, then the curl of the fingers is in counterclockwise direction, which is the magnetic field as I described, and the current is in upwards direction, as you can see with your thumb. So this is a straight, simple current carrying conductor. There is another one which is called a solenoid, right? And it's nothing but just a wire that is kind of curled in a spiral like this. So it's still a wire, but it's curled in a spiral like this. Now, suppose if there, if I have this wire, right, and I can connect it to some battery so that there is current across this wire, then suppose if the current is in this direction, so it's going like this and then going like this, and so there should be magnetic field around this solenoid as well, because the charges are moving